I realized I was supposed to be talking about architecture, and it's rather odd that I reflected for a while, trying to remember what an architecture was. And that's what I think it is. I was sort of taught this when I was quite young. You know, it's supposed to be something that's quite fixed for a range of implementations over a period of years, and that the programmer and user of the architecture and the series of machines based on it can understand it all and rely on it. Okay? In other words, it's not something that's supposed to change every 6 months because an extra few instructions have been dropped in, or an extra sort of few threads, or this, that, and the other. Okay, so you can see the world's changed quite a bit since I was young, because actually we have architecture version 1, version 2, version 7, version 6.5 of every core you can think of. Okay, and new ones rolled out all the time. Okay, however, I still believe this is what architecture is all about. It's about a contract essentially between the makers of the hardware and the people that use it, and it's supposed to make life easy for both sides. Because if the architecture is well conceived, then the machine implementers can carry on implementing better and better versions of it without messing up all the software and changing the economics of the software and causing it all to have to be re-optimized and ported around. So this talk is going to be about why I think we should try and make things simpler. One interesting thing that's happening is that actually over the last 20 years and up to now, you know, our main architectures that we've been using, we're talking about world design for PCs. They're based on computer technology, turned into PCs in the 1970s and 80s, and then actually sort of optimized and optimized and optimized in various ways over the period from then until now. We've been improving on 1980s technologies, essentially, or possibly even older ones, you could argue. And that's been enabled, really, by this sort of Moore's Law thing, massive growth in the PC market, which sustained sustained Moore's Law, which would only have been possible. The investment in sustaining Moore's Law has been enormous, but it's been justified because of that market. Okay. Actually, most of the techniques we've been using in the 1990s and so on date from a long, long time ago. The superscalar stuff is back in the 1960s. So anyway, with that enormous momentum behind these architectures, they've been deployed everywhere because they were cheap and easy and available. It was simply made it impossible to justify building special purpose designs optimized for things like HPC, clouds, clusters, mobiles, wearables, and so on. But everything, of course, is now changing. It's changing partly because the PCs are an endangered species. The sales of those are dropping rapidly, so it's not obvious any longer that this is going to drive an enormous volume of processors optimized for PC-type functions. What we now need is something rather different to do our clouds, wearables, things, robots, and whatever. We need proper scalable multiprocessing, both on chip and in the big systems, in the clouds. That comes down, as I've said many times, to lots of interprocessor communication. A lot of the challenges are in the interconnection networks more than the processors, but even the processors, you've got to be careful about the design for doing parallelism. We also, in things like Internet of Things and robots and things, need lots of responsive input and output. This was not something that was characteristic of early computers or PCs. There were relatively few communication channels, but now there are going to be lots. All of those things are going to be connected to physical devices. Some of them will be hard real-time, some of them won't, but it's going to be very input-output focused and communication focused. And we're going to need to focus on software efficiency, in my view, both for the multiprocessors and for the Internet of Things. The Internet of Things is not a new idea. Actually, 10, 15 years ago, we used to talk about ubiquitous computing, meaning roughly the same thing. And actually, 10 years ago, there was an idea that things like Zigbee were going to take over the world. We're going to have light switches that were wireless and so on. There were even one or two produced. Okay, it's not that easy to make that work. The technology is easy at the hardware level. It's the software that's a problem. Your electrician is not going to turn into a system maintainer in the software and computing sense. Okay? So you've got to really make this work on the software, make it reliable and robust. So there's a lot of development to do there, and in some cases I suspect quite a lot of software is going to need to be packaged into a very small space, consuming a very small amount of energy. And those areas, both multiprocessing and responsive input and output and stuff, needs predictability in the computing. And that's timing, power, and energy. We need to know how long things are going to take to execute, how much energy they're going to take, and how much power they're going to take. So in other words, this is not just about writing the program and hoping for the best. Timing matters all over the place. It obviously matters in hard real-time applications, but actually it's hidden, the requirement for this in parallel computing. There are lots of potential sources of timing jitter in parallel computing, in the processors, caches, memory, interconnects. And we have to manage latencies in communication in our software, and you can't manage latency if you don't know how big it is. We also find, of course, that we have these synchronization barriers in control flows, data flows and stuff, and those are delayed by the slowest participant. And we may need to put buffers in and so on when we're doing stream processing. So just to show you what that means, some of you will probably have seen this slide before, but basically if you've got a probability of no cache miss when executing a program, and you execute lots of copies of this program in parallel, terminating at a barrier, then this is the probability that you're going to get a delay. And actually the probability of no delay. And as you see, for 100 processors, we've got a pretty good chance that we're going to get delayed. For 1,000 processors, it's guaranteed. So if that delay of one component causes a significant factor, a factor of 2 maybe, or a factor of 10, then you're going to lose the value of all the processors. So that's why jitter in sequential execution is a problem for parallelism, and in interconnection network contention will have the same problems. So to build good parallel machines, we need predictable components and predictable networks. These are my favorite programs. I'm not going to go into them in any detail. As you can see, they're all the same, almost. Okay. They all compute exactly the same thing, but they take vastly different lengths of time today. In 1980, the programs would have had almost the same runtime. Today, on the state-of-the-art machine, the difference is about 50, caused by variation in access time to the memory hierarchy. They're a bit contrived. One of them actually effectively disables the caching by choosing the ordering of accesses to memory. And another one actually effectively disables the superscalar execution. But this, of course, means that, that anybody trying to program using modern machines with modern programming languages actually doesn't really know how fast the program is going to go. And if you start running lots of them in parallel, you get all these kinds of problems potentially that I've just referred to. The parallel machine won't work very well. I did have a quick look, and actually this is actually slightly worse than the EDSAT, the 1949 machine, the first practical stored program computer built in the world, which used mercury delay lines. If the data had just gone past the end of the delay line when you wanted it, you had to wait for it to go around again. So now I do remember the designers of the EDSAT saying what a fantastic revolution it was when magnetic core memory appeared, because it meant they could go to a flat random access memory structure and get rid of all these problems. So we seem to be back there again. Anyway, so I don't believe you can build efficient software for unpredictable machines. Parallel composition, putting lots of things together, is an absolutely essential programming tool, and it's supposed to mean that when I take two tasks, A and B, I know what the performance of both is, and I put them together, nothing weird happens. Okay? Efficient versus parallel computing, this is the real takeaway, are not the same as efficient versus for sequential computing. For sequential processes, you optimize for the average case, and that's fine. Okay? For parallel computing, you can't do that. And sharing the memory hierarchy makes things worse. Okay? You get more contention for the cache lines, so actually, strictly speaking, you should scale up the cache associativity with the number of threads or cores that are accessing the cache. Just check out when you're about to sign up to buy a multi-core, whether that's actually been done properly by the designers. Then we have the coherency protocols, which are incredibly difficult to understand, and certainly it's difficult to understand the real-time effects of them. And these are then often used to implement synchronization and sharing using memory operations. A strange situation to be in. The hardware passes messages around. The messages are used to implement coherency protocols, which are used to implement shared memory. And on top of the shared memory, the programmer quite often will build message passing. Why? We put 2 layers of abstraction in order to get back to where we should have been. And then there's another little snag that I only realized a short time ago. When you look inside the DRAMs, the actual main memory, somebody else has done some clever stuff. There are some hidden caches there, the 64 kilobit page buffers. Okay? So once again, you'll find that potentially there is an issue that the order of access to the memories will have catastrophic effects on both the timing and energy of the program. Okay? So it affects all of those things. The programmer has no idea what's going on, by the way, unless he's a real expert on computer architecture and microarchitecture. And then, well, I mentioned the importance of communication input and output. Pipeline superscalar processes take a long time to respond, even if they have only a 9-stage pipeline. So communication ends up being offloaded to hardware, input-output is offloaded to hardware. But then what if you need a programmed response to the external event? Then you need the processor to wake up and do something. And in practice, offloading in high-performance computing often means that the hardware only deals with very long messages efficiently. Well, we have some schemes for this. We try and hide complexity with abstraction layers. They normally mean that you've no idea about the efficiency. And then when we try and do some hiding with tools, we end up with all kinds of fancy optimizations provided by tools or compilers, 100 flags or so, for modern GCC and so on. How to set them has become a research project in some universities. What 100 flags guarantees is that most combinations are untested. You couldn't possibly depend on them. Tony Hall made this comment a long time ago in a slightly different context. We've seen it all. We are wasting people. Every abstraction layer has the potential to waste energy and time and increase the programming costs because people have to worry about it. We've got scarce, highly skilled people coping with architectural complexity that shouldn't be there. With university groups trying to make sense of it all, especially now we're trying to understand timing and energy. But, you know, everything's good news from here on. Moore's law is now at an end. It was really at an end 5 or 10 years ago, but people were persistent to try and keep it going. It's now clear that we're not going to see some of the things that people were hoping for. Exascale is not going to happen by 2018, no matter how many governments try and pour money into it. And actually a better target will be to make programmable machines anyway. It's the scientists and engineers that should be programming these machines. It shouldn't need a computer scientist and computer architect to tell them how to do it. But it currently does. If you take scientific codes and actually get an expert on trying to optimize them, they will always find a factor of 10 because they go and look at how the machine is sitting on top of the architecture. Of course, there was no very good reason for this target apart from Moore's law, because there's no particular scientific advance that's held up waiting for 10 to the 18th block. Not that I know of, anyway. And the other thing, I've sort of hinted at this, we're not going to be able to build wearables and things by sticking lots of stuff together and waiting for Moore's law to help us, okay, which has been a fairly traditional way of developing software for the last 20 or 30 years. Okay. Some of these things will be involved in controlling infrastructure. They've got to last for a long time. They've got to be trusted and reliable, which is going to be difficult. And actually, as Tony also said, the price of reliability is the pursuit of simplicity. Price that the very rich find most hard to pay. That still seems to be true, actually. So, some years ago, I realized I'd given a talk like this called The Return of Innovation. This is 10 years ago. This is The Return of Innovation 2, and it makes some further similar points. We are going to need reliability along with power and energy efficiency. We need to package technology and make it easy to understand and use. It's the software and application developers need as much help as possible. They need easy-to-use stuff. They've got to deliver all the software that makes this work. We need portability, again, without having to re-implement and retune from one thing to another. I was astonished to find this term performance portability. That used to come for free because machines were all similar enough that you knew that if you'd optimized a program for one machine, you could use roughly the same optimizations on another. This no longer works, especially for GPUs. You just have to go and take do the whole optimization job again. Okay? And actually, nobody's talked about energy portability, I think, but that will become an important issue too. When I've optimized the thing to make it as energy efficient as possible, I want to use the same techniques and just move the stuff around. It raises an interesting question as to whether some of the relative costs of operations should be part of the architectural specification. So in my view, software efficiency is the key issue for the next few years in the cloud's wearables and things. And just to point this out yet again, I think I put this slide together 10 years ago, software efficiency can make massive inroads into energy and time and everything. If you reduce the number of operations from n squared to n log n, for large n, the effect is dramatic. In fact, for 30 billion, the change is as good as 50 years of technology improvements. Okay? So having people sitting and thinking, writing decent software on top of decent architectures looks like a good idea. I've nearly finished. So, general purpose parallelism, predictable interconnects, predictable execution, predictable caches. If you want to put caches in, you can make predictable caches. I'll tell you how to do it. Multi-threading, or plenty of resources so that interrupts have negligible effect. Programmable interfacing, which means horizontal execution, not pipelines. You've got to do several things at once to do that fast. And actually, some of these asynchronous techniques are probably worth a look again. Nothing responds faster than a processor whose clock is stalled. The cloud we're going to be using for a variety of things, all of these certainly, a lot of algorithms and techniques. So actually you want scalable general purpose parallelism. I mean, it's okay to specialize once you know exactly what you're doing, but if you specialize the hardware too quickly, you're taking away the freedom of the software developer to find good and better algorithms and to change them all the time. And actually, most of the focus on this stuff, in my view, should be on data movement. That's the key factor. It's usually the limiting factor in HPC. And actually, if anybody wants an exascale target, I'd suggest 10 to the 18 interprocessor operands per second. Forget the flops. And in the wearables and things, they will need high instantaneous performance, vision embedded intelligence. They'll have to be very energy efficient. I think it will be innovative companies that do where most of the action comes here. And in order to empower those people, we need to give them easy-to-use technology they can play with. Real-time, energy-efficient, power-efficient, small, long-lasting, it's in infrastructure, and easy to use. I'll skip this one, but you can read it if you like. Robotics I have to mention, because we have a huge robot lab just there, and I think robotics is a great topic for using lots of processors. It's already been mentioned today. I found this rather nice quote about the number of muscles in the human body, and I thought it was would probably suggest that we could sell an awful lot of chips there to control them all. So I have two projects on the go I'm going to mention. I mentioned this one last year. I'm still working on it, partly because I'm determined to teach a load of students how easy you can make parallel computing. But I would actually quite like to build one of these, especially with the non-blocking network in the middle of it, to make all the programming really simple. And the other project I'm interested in, and it's topical, is this one. Actually, 2015 is technically the time at which the thing was really launched to the general public in large quantity. So we've got a bit of time to do this yet. But I would really like to reconstruct this device. And the reason it's topical in terms of what I've been talking about is that the ultimate original motivation for building the transputer and designing it was to simplify design. It was to build a new kind of component which will make it easy for system developers and software people to build complex systems. Thank you.
So we do have time for one question.
Really?
Yep. I lied to you about the time.
It had to be you.
Yes, it would be. Dick Selwood, EE Journal, and ex-Inmos. You've said software efficiency is going to be the key. The vast bulk of software around the world is written by people who bodge together programs, and if they compile, move on to the next program. How the hell are you going to improve that?
Well, I don't think I have to do anything. They've only been able to get away with that because of Moore's law. And we don't have a solution. I mean, you're absolutely right. I don't think this is a change that will happen overnight, but unless something miraculous happens, then the world is going to have to change. I mean, at the moment, I mean, I watch students doing this. They'll pull a great pile of stuff off the internet, hack it all together, and if you know, that's it. That is the way people build software. That's what Moore's law has enabled. You know, massive amounts of memory, so you don't have to worry about how much space is taken up, and really, you know, a hell of a lot of performance relative to what they used to be. Interestingly enough, if you actually do take fairly old-fashioned software, like the kind I write, and run it on modern machines, it's spectacular. You know, when I did compiler development, compiler bootstrap, and I used to press return and go for coffee. Okay, if I do it these days, I press return and the prompt is up there straight away. Of course, if you're a GCC developer, you press return and go for coffee.
Okay.
I mean, the point you make is very interesting, and you're right. People do just hack stuff together and go with it. But actually, you know, if you want it to increase performance and you want to achieve some of these Internet of Things things, you've got to put a lot of software into a very small space. A lot of them are actually, the things that are out there that people say are going to happen are actually not achievable without some big changes in software development and development approaches, actually. I mean, you see your temptation is to just take the whole bloody stack, all the Linux stack and the protocol stack and everything, and lob it inside some tiny device, and let that deal with the problem. I think they'll work.
I think you hit a pet subject there. I'm going to have to time out on that. Of course, you have to find somebody who can test your software properly as well. Just one answer as well.
Yes, absolutely.
So anyway, thanks very much.
All right, cheers.